Okay, so we're going to take a look at chapter 10, trigonometry, and I'm going to start off right at the beginning, 10a and 10b. Now, we're going to start talking about this first one here, exact values. And if you've got a good memory, you might remember these from GCSE. Very useful to know, though. We'll talk about why you should know them and not just use a calculator instead. I might suggest clicking on this link as well. There's a very, very good demonstration for the exact values. I'm going to show you some different ways today, but this I found to be a very good video for it as well. And then in the other parts of the video, we're going to do some sort of proofs. If you did further maths at GCSE, you will have dealt with this before. It's more or less identical, really. We're going to do 2 videos on solving equations. So what does that mean? That means sort of going backwards. So we're going to say, what would be an angle? What would be a value in degrees that would give me a certain value out of my graph? And what's interesting about this is that there's multiple answers to that question. And then the last part, we're going to link to all that work we did on quadratics, because actually we can combine that chapter and this chapter together. Okay, so let's start off by talking about 30, 45, and 60 degrees with sine, cos, and tan. And you'll see them a lot. Why? Because, well, think about 60, we have equilateral triangles. 30, if you sort of cut one of these triangles into 2, which you'll just see in a second, you can end up with 30 quite a lot. And 45 is, sort of a right-angled isosceles triangle. So, these kind of shapes here. Okay. And you can derive these yourself. So one way you can do it here is if you use a square in your book, 1 by 1, the hypotenuse will be √2 because of Pythagoras. And then this angle here is 45. And then sine, cos, and tan, well, you'll remember from SOHCAHTOA, sine, what is sine? It's the opposite over the hypotenuse. So 1 over √2. And you get your answer. For cos, it's pretty much the same. And tan, what is tan? Well, tan is opposite over adjacent, 1 over 1. So those are the key values for 45. Okay. What else can we do? Well, we could talk about 30 degrees. So if we drew an equilateral triangle, so all of the sides were 2, and then we cut it down the middle. That would be just 1, wouldn't it? That would be a 60-degree angle if it's an equilateral triangle. And this must be 30 then. It's been bisected, so 60 divided by 2. Pythagoras, to find the short side, 2 squared minus 1 squared, square root it, you get √3. So again, this might sort of ring a bell from GCSE. If we pick 30 to concentrate on first of all, so from the perspective of 30, sine is, well, you go back to SOHCAHTOA again. So sine is opposite. What is opposite? Well, it's a 1 over hypotenuse is 2. So 1 over 2 or a half. Okay. Cos √3 over 2. Okay. And, you sort of get the idea. For 60, you can then switch your perspective. So it's not from here anymore, but from this 60. Sine, we just said, is opposite over hypotenuse. So opposite over hypotenuse. Okay, and so on. It's worth saying while we're here as well, you may have sort of learned to write these in different forms, for example. So if you rationalize the denominator, in other words, if you multiply the top and bottom by the square root of 2, you'll get an answer that looks different, √2 over 2, but this has exactly the same value, okay? And the same for cos. So either form is acceptable. Now, you might sort of ask yourself, why do we need to know these? Well, the reason why we need to know them is because when we have harder questions later on, we need to sort of, when we get asked to show that, for example, and we see this, we need to be thinking in our head, where is this going to come from? And it helps give you a great understanding of how to solve the questions. So if I see something like this or something like this as a final answer, I know perhaps that I need to do something with trigonometry. That's just one reason why you need to know this. The other idea is this will actually be relatively simple compared to some of the stuff that you're doing later. So you really don't want to be wasting time with this. A final answer, later you will learn to measure angles in a different way. And if your calculator is in the wrong mode, it will give you complete gibberish. So you don't want to rely on your calculator for this. It's fine to check, it's good to check, but you need to know these values in another way as well. So I'm going to actually do a little demonstration with the unit circle. And what the unit circle is we're going to make a circle with the radius of 1. Okay. And let's show you something a little bit more dynamic so you can get an idea what's going to happen. So let me just check first of all. So yeah, I'm going to start with this. So this is my unit circle. So if I go like, let's do 30 degrees, shall we? If I do 30 degrees, I've got a hypotenuse of 1. I've got an angle, and I'm making this angle here with the x-axis, okay? And I'm just making a right angle triangle. And this will go all the way around. This will go all the way around because it's a circle, okay? So if I do something like this, 30 is a half. We expected that, didn't we? 60, well, just going back to what we discussed a second ago, 60 should be, sine 60 should be root 3 over 2. So if you check for yourself with a calculator, you'll get this value here, 0.866. Okay? And what I'm going to concentrate on in particular with this is this red line. Okay? So why is this red line being shown? Well, let's go back to something we can write on now. If we go back to this one here, and we start making some statements from SOHCAHTOA, have a look what happens. Sine of theta, so why am I doing this? I'm just sort of showing you what happens when you have a 1 here. Sine theta equals opposite over hypotenuse. The opposite side here is this part, isn't it? The height, yeah? So I'm going to say the opposite, and it's over the hypotenuse, but the hypotenuse is just 1. So if you look at your equation, what you're left with, you're left with quite an interesting result. The opposite side is actually the same as sine theta. Okay? And this will be true. This will be true anywhere, for any angle, for any way you drag around this circle, because the hypotenuse will always be 1. So the height in the unit circle tells you sine theta. And you can probably guess where I'm going with the next part. If you make a cos statement, cos theta is adjacent over hypotenuse. And again, hypotenuse is 1. It's always 1 in a unit circle. That's why we use the unit circle. That's why it's useful. So we end up with this result. The adjacent side is actually the same as cos theta. So I could just call this the opposite side and the adjacent side, but it's more useful if I write them in terms of sine theta and cos theta. Okay? And while we're at it, what is the gradient of this bold line? Go back to chapter 5, straight lines. How do you find the gradient of a straight line? Well, it's the difference in y's, which is sine theta, divided by the difference in x. Okay, and this is actually the same as tan theta. Why? Because for TOA in SOHCAHTOA, if you do tan equals opposite over adjacent, okay, you will get this result as well. So quite a few interesting things going on here that we can make from our triangle. So the main ideas are this: the height is sine theta, the width okay, is the horizontal distance, I suppose, is cos theta, and the gradient of the line shows you tan theta. So for example here, because the gradient of this line is clearly positive, tan theta would be positive as well. Okay, so let's do a demonstration with that. So we just said we now understand why the red line is being looked at here. The radius is 1. So if we do SOHCAHTOA for sine, opposite over hypotenuse is the red line. And I'd like you to look at how the red line changes as I go from 0 degrees to something more. So let's do 0 to 30 because we know that. And if I trace each of those movements, it will give me what I've got here on the right-hand side. So it's going up quite quickly to begin with. Let's go to 45 now. Well, 48 is a little bit difficult. 45 seems to be slowing down just the smallest amount. To 60, again, it seems to be slowing down. And I encourage you to take a look at the circle. Have a think. As we spin around this, making this angle bigger, this black line here, what's going to happen to the height? Well, can you see? It's going to go up to 1, isn't it? Now, I'm going to keep going. So I'm going to keep going sort of anti-clockwise again and again and again. It's now going to go down, isn't it? Because the circle doesn't go any higher. There's no way it could go any higher. And here's my red value. A couple of things to notice. Notice, first of all, that it's still positive because it still has a positive sort of, I suppose, we could say height, but it sort of has like a positive displacement to it. So it's still a positive value, even when it's on this side. And you can probably spot some symmetry as well. If I have 150 degrees, I get a half. And I seem to remember I got a half when I put in 30 degrees. In fact, let's just check that, shall we? So when I put 30 degrees in, I got a half. And when I went to 150 degrees, I get a half as well. So there definitely seems to be something going on with using values, over 90 degrees. We can link them back to values for, acute angles. Now, what's going to happen if I go here? Well, I'm going to get to a 0 point, aren't I? Which is 180 degrees. So on my graph, that's what sine looks like. And I keep on going. And again, there's some more patterns. A half, 0.5 is coming out again. 210 to 180. We're thinking about 30 again. 30 seems to be important. What's the lowest value? Well, the circle only goes down to -1. So -1 at 270 degrees. And then we finish off. And what we've derived is the sine theta graph. So this is what the sine theta graph looks like. Okay. We go from having no height to some height to some more height, a maximum there. And then we lose some of that height. We lose it. And then it goes to 0. And then we have a negative displacement. And we will get the maximum negative displacement at -1. Okay. And 360, we are back at the start. And actually, I could keep going again. And I would just repeat exactly the same journey. So while we're at it, let's talk about cos. Notice here, the pink part has been highlighted. When we did SOHCAHTOA and we made a cos statement, we had adjacent over hypotenuse, which was 1. So we're now looking at the pink line. What's one of the key differences? Well, when you start cos, it seems to have its maximum value already. Because look, the width is at its maximum here, isn't it? You're as far over to the right as you can be at 1. And as we make our angle bigger, it's not going to be quite as far. It's not going to be 1. In fact, you're sort of falling away from the edge there each time. And then at this point, there's no across component because you're on this axis. So you reach 0. Okay. You're as far over to the left as you can be after 180. So that's why there's that -1 there. Notice 1 and -1 again between these numbers. Returning to 0 again because it's 0 across. And then all the way over to the right, which is a 1. So it reaches its maximum value there of 1. Okay. In other words, cos is like a journey of starting at your maximum and immediately falling away. And the shape, notice this wave shape here, exactly the same as before. Okay, so we're just getting a bit more of an intuition there for where we get some of these values from. And this would have been covered a bit in the previous chapter, but I will keep going back to these shapes here. So you need to learn these shapes very, very well. Okay, so we're imagining now, as we rotate around, what happens? So when we're between 0 and 90, well, cos was our x value, sine was our y value. So in other words, this was like our width and our height. And then tan is the gradient. So we're just looking at whether the gradient is, positive, negative, 0, something like that. So what can we say? Well, we have height and we're also across. So they're both going to be positive. Tan is going to be positive as well. So everything there is positive. When we're at 90, that means we're pointing directly upwards. We will have a height of 1. So sine theta will be 1. The width, the x value, well, will be 0 across. So cos will be 0. And what will be the gradient? Well, what's the gradient of a line that goes vertically upwards? So no width, the maximum height, which is 1. Okay, and we sort of say that this is undefined. You might remember having something like x equals 0. That's normally how we talked about a line like this. As we move over a bit more, we're still going to have a height, which is sine, so that will be positive. We're over to the left, so our x value will be negative, cos will be negative, and the gradient of the line is -2. So I'd encourage you just to pause here and to think carefully about these remaining ones, what their values would be. So you might just need to be general and say positive or negative, or if there are any special values here, that would be 1 or 0. And I'm assuming you've done that. So let's have a look at the results. And I'm not going to talk through these because I feel like you can have a look back. I've probably been fairly repetitive at this point. Okay, so here's the sine graph, and we know where this comes from now. So let's have a look at some rules. So what were some rules that we picked out? Well, one of them, if you remember, we noticed that when we got 0.5 for sine, another place that we got that value was over here on the right-hand side. We got it at 150. And I'll sort of give you another example. When you do sine of 45, you will get the same value as when you do sine of 135. So what's going on here? Well, yes, there is some symmetry down this sort of line here in the middle, but how could we describe this with a rule? So if you put in, if 30 gives you the same value as 150, 45 the same as 135, what do they add up to together? Well, it's this rule here. So you can find a value by doing sine of 180 minus the other value. So for example, you can find sine of 150 by doing, well, that's kind of the other way around. I suppose you could do sine of 30 by doing sine of 180 minus 30. So sine of 30 is the same as sine of 150. And that's what this diagram is showing us. So this is one of the key rules. Cos also does the same thing. So if we took a bit more time, we would notice that these values would be the same. They have the same height, the same y value. So this is the rule. This is the rule to find the other angle that goes along with it. Okay. These are sort of the two main ones, but we also noticed that because we had a circle and because angles around a point are 360 degrees, we repeated our journey every 360 degrees. So why are we doing this? Well, we're doing all of this because it's important to make sure that you don't miss out on any answers. So if we want to know which value would give you a half, for example, it's not enough to just look at 30. We need to look at 150 as well. Depending on the question, we might need to look at, well, 390. We might need to add 360 on. We might need to add another 360 on there as well. It depends on the question. So we need to know that many angles can give us an answer. Careful with tan though, okay? Tan is a little bit different, okay? Because tan was given by the gradient, if we have a look here, this is the shape of the tan graph. We notice that this occurs exactly 180 degrees after itself, okay? So it repeats every 180 degrees. Okay, and finally, this one doesn't come up an awful lot, but there is the rule that sine of x is equal to cos of 90 minus x, and this is all to do with what cosine actually means. Cosine means that it complements sine; it goes along with sine. So if we look at the next slide, if you have complementary angles, these are called complementary angles, A and B. You can see that they add up to 90. Well, if you had a parallel side there, okay, let's go like this. This is a Z angle. So this one's B as well. In other words, you can sort of have A and B occurring together in a right angle triangle. These will be complementary angles. And when we had a situation like this, let's just show you, for example, cos of 50, cos is your adjacent over your hypotenuse, so x over y. Sine of 40, if you change your perspective and you measure from this angle over here, opposite over hypotenuse, this is also x over z. So if you take cos of 50, it's the same as doing sine of 40. If you did cos of 60, remember, is a half. That would be the same as sine of 30. Sine of 30, remember, is a half. So this is a lesser sort of discussed rule, but this is one that we need to be aware of as well. Let's just have a quick check how we are for slides. So a couple of quick ones here. We need to use these ideas to make these questions simpler. So tan, this is a very large number. Perhaps we could take 180 off it because it repeats every 180. So it's the same as tan of 45. Sine of 150. For large numbers, you can do 180 minus 150, sine of 30. Cos of 300, we could do 360 minus, so it's the same as cos of 60. Sine minus 45, lots of ways that you can do this. Let's have a look to see what they do. Aha. So if we'd extended our graph a little bit to the left, sine is what's called an odd function as well. So if we go to the left by 45 and we get this answer, it's kind of the same as going to the right by 45, getting this answer, and then putting a minus in the front. Okay, so that's another way that we can sort of use these diagrams. Cos of a very large number, well, I'm going to take away a 360, and 720 is less. I'll take away another 360 as well. And cos of 120, what could we do for this one here? Well, cos of 240 doesn't really make it that much easier. Let's have a look to see what they do. So they've sort of drawn out their graph here. 120 is down here. So really we're using the same idea as up here. Okay, you might remember I talked about 30 degrees when we looked at 120. It was all about 30 degrees. So if you go back to the left 30 degrees from 90, you get a half. Well, however much you go up by is the same as if you go down by to the right. You just need to make it a negative. Okay. Of course, you can also verify all these values with a calculator too. So a lot of properties we're discussing then. These ones here on this page, these will be the main ones to know. Okay, and there are a couple of exercises in the book. Just a word of warning in 10A and B, they often use something called the cast diagrams. I haven't shown that to you today. There's also many other techniques that you can use as well to make sure you know these key values.